All right, so we are going to discuss the examination of network dynamics using random walks. I'm Neo Ogilvy.
I'm Peter Larson.
All right, so just an overview of what we're planning on doing. We're just going to talk about what we're modeling, how we modeled it, the results, and then further steps. So what are we modeling? In part one, this is set up in 3 separate parts. In part one, we are doing comparisons using random walks between a standard 3D space and a non-uniform dimensional network. In part two, we're going to look at a random walk with specific origins based on centrality within our non-uniform dimensional network. And in part three, we're going to look at navigating a network with random walks while including bias for paired networks. So how are we modeling part one? We basically created a network of Marvel comic characters, and using adjacency matrix and linear algebra, we've come up with a network that is randomly walked. Below, we'll look at 2 graphical representations of the person-to-person network from that Marvel comic universe. The first one here being generated in Python using the backward package network X, which is what's doing all of our manipulation. The second one here is a representation from Gephi. This one, the nodes have names next to them, and the groups are colored, as seen in the chart. It's hard to see the names, obviously, because it's a pretty large network. But moving on, how is it being modeled? So to start off in part one, we select a random node, and from there, we will randomly move to a neighboring node. We perform this movement 1,000 times, and to kind of smooth over irregularities and average all results, we iterate that 1,000-time walk 100 times. Just for future reference, this is denoted as a non-uni for non-uniform dimension and degree. We'll basically see that later on in this presentation. On the right here, you can see a picture of our network and it being randomly walked, the red being edges that have been walked. In this case, this is after 100 steps. 1,000 steps is a little confusing to see. So for our comparison, we wanted to have a standard 3D random walk. So very similarly, we had it just walk in random directions for 1,000 steps. And then to smooth over irregularities again, we iterated that 1,000-step walk 100 times. And for future reference, this is denoted as uni for uniform dimensional degree. And on the right here, you can see a picture of 1,000 steps that have been walked over in a 3-dimensional space.
In order to compare the uni and non-uni random node walks, we implemented 2 metrics: coverage fraction, which measures the amount of unique nodes visited for each run, and rate of return, which measures the overall success of the random walk returning to its origin at some point in the run. Based on the work by the 7 people listed here, it can be mathematically shown that the rate of return for a standard 3D random walk is about 34%. So the coverage fraction, or CF, for the uni runs was 67.41%. The coverage fraction for the non-uni runs was 73.13%. This means that on average, the random walk in the P2P networks was reaching approximately 57 more unique nodes per run than the 3D random walk. The rate of return for the uni runs was 34%. The rate of return for the non-uni runs was 44%. This means that aside from our results for the 3D run matching near perfectly with the mathematics, a non-uni run was 10% more likely to return to the origin at some point within 1,000 time steps. Here we can see a graphical representation of all 100 runs for the uni in blue and the non-uni in orange. As we can see, the uni are more spread out over the range from around, I believe, 582 to 746, whereas the non-uni are clustered, everything above 700 only going to 755. Part 2 we modeled, but instead of starting at a random node, we start at a specific node based on centralities. Those centralities we'll explain in a bit. Then we perform the movements exactly the same, 1,000 movements, ideally over 100 iterations. There are 3 centralities we chose, betweenness centrality, closeness centrality, and eigenvector centrality. Betweenness centrality essentially measures how often is a node on the shortest paths between any 2 nodes in the network. Closeness centrality measures the average distance in path length from a node to every other node in the network. And eigenvector centrality measures how close it is to other central nodes. So our results, we looked at the top 5, middle 5, and bottom 5 for each of the 3. As we can see here, the middle 5 is greater than the top 5 for betweenness. Unsure why, but we will get into potentials later. For the eigenvector centrality, here the top 5 is greater, but the bottom 5 is better than the middle 5 at reaching more unique nodes. Again, we will cover why these might be in a bit. And finally, for closeness, this is the first one and only one that properly tiers top 5 better than middle 5, better than bottom 5. Reasons for some of these might be the fact that we weren't actually able to have the time to do the 100 iterations for each member of the top 5, bottom 5, and middle 5 for each of the centralities. So there's the potential that some of these or all of these are outliers in our system. And so our goals in the following week before submission of the final paper will be to perform the 100 iterations to try and average out and remove those irregularities. Also, rate of return is kind of a bit silly to do at the current stage, simply because with only 5 runs for each category, you aren't really able to compare each, as 5 is not large enough of a sample size. Finally, part 3 is the part we have been able to do the least of, just based on time. Using weights from the other network. The other network was created, as I explained, A transpose A gives us group to group. We want to guide a random walker by influencing the adjacency lists in the P2P network with the weights from the group to group network. So we designate one random group as the origin group, and then another random group that is not our origin as the target. We then select a member of the origin group randomly such that they are not a member of the target group, and alter their adjacency lists based on the weights. On screen is an example of how those adjacency lists would be edited. Essentially, in the normal stance, you would have an equal shot of going to B, C, D, E, and Z. In the altered stance, you now have 11 chances to go to C, no chances to go to E, and 1 chance to go to D. And so everything is altered based on those weights from the group-to-group network. As I currently said, we are still trying to develop these. Our current problems are the fact that several CSVs aren't loading in properly, and so we aren't able to take stuff off of them. And we will be hoping to correct this over the weekend.
So to wrap it up, we've basically been able to create a network of Marvel comic characters using adjacency matrix and linear algebra manipulations, and uploading that data to our Network X and Jiffy packages. We were able to implement and test random walks for uni and non-uni networks in part 1, and that's been wrapped up. Part 2, we've been able to implement and test the random walks for pre-selected nodes in our non-uniform network, but there are some more tests we'd like to run. And then finally, part 3, we've started implementing the model, and we'll hopefully have results shortly.
Perfect. Thank you.